Thank you so much, Jenny. So today we are thrilled to welcome Karthik Kashinath, who leads various climate informatics and machine learning projects at the Big Data Center at Lawrence Berkeley National Lab. He received his bachelor's from IIT Madras, his master's from Stanford University, and his PhD from the University of Cambridge. His research uses the power of machine learning to accelerate scientific discovery in the complex chaotic systems of turbulence, weather, and climate science. And a particular focus area is physics-informed machine learning to develop physically consistent, trustworthy, and more robust machine learning models. Which brings us to the theme of today's talk, physics-informed machine learning for weather and climate science. And with that, I'll give the floor to Karthik. Thank you for coming today.
Thank you very much, Tom, for that kind introduction, and thank you all for joining this seminar today. Thanks also to the US ClimateNet Data Science Committee for inviting me to present on this topic. This topic is probably familiar to many of you, especially after the great seminar that Professor Vipin Kumar gave 2 weeks ago on a very similar topic. So hopefully this will complement some of what he shared 2 weeks ago. In the attempt to sort of encompass a wide range of applications, I have compromised on depth and I'm trying to give you more breadth, but I'll be happy to get into details as we go along in the Q&A. So please save your questions for me. With that, I'll get started. And as Tom said, the topic is physics-informed machine learning, and I'll try to argue why incorporating physics is important for applications of AI in weather and climate science. So a quick roadmap for my talk. I'll introduce machine learning for weather and climate and the unique opportunities that we have, a brief overview of the types of research topics that I've worked on, including methods, applications, complexity, and scale. Then I'll have a deep dive into two topics, one on pattern recognition for extreme weather phenomena, and the other is on space-time super resolution for complex flows. And then I'll try to sort of conclude with some speculations on the future of physics-informed machine learning and challenges and opportunities that we have as a community. So we've seen in the last couple of years some significant breakthroughs in the sciences thanks to the AI revolution. It's been recognized widely by sort of all of the leading journals and research societies that this is a remarkable time for us in applications of AI to the sciences. On the top left is the protein folding breakthrough recently from AlphaFold. In medicine, we've seen significant breakthroughs in physics and chemistry, synthesis of materials, and so on. But I would like to argue that we do need to incorporate physics and domain knowledge to really build reliable, trustworthy AI models for weather and climate. And hopefully, by the end of this talk, you'll see why that might be a convincing vision. Some of the applications to which we can apply AI, and in particular physics-informed machine learning, are pattern discovery in large data sets for a wide range of phenomena in the weather and climate systems, emulating complex processes that are in operation in the atmosphere and the ocean in various other processes, downscaling data, so increasing the spatial and temporal resolution of weather and climate data, accelerating simulations so they're actually tractable, and finally improving forecasts to improve skill but also reduce uncertainties. So getting into the deep dive, the first topic I'd like to focus on is on recognizing and discovering patterns. You'll see here quite a lot of information, but I basically tried to map out the 5 different application areas that I just mentioned, the different methods, the physical complexity of the systems these have been applied to, and the computational scale. So for the first deep dive, I'll focus on recognizing or discovering patterns. The techniques will be from deep learning and computer vision. The complexity is applying it to global climate data, both model output and observational data. And the scale is order of hundreds of terabytes and thousands of CPU or GPU nodes. The second project will focus on downscaling data, which is also known as super resolution in the machine learning community. And this uses custom deep neural networks. The physical process that we apply it to is turbulent convection. And this is a slightly smaller scale with terabytes of data and hundreds of GPUs. So getting into the first topic, which is pattern recognition, the sort of title for this topic is ClimateNet, and this is in collaboration with folks from ETH Zurich on the computer science side, from UC Berkeley on climate science, and several other scientists at the lab, at Lawrence Berkeley Lab, that have worked on this over the years. I think the motivation for us as a community is very clear. Of course, many of us have been working in this area for a while. But just to summarize, detecting and tracking extreme events is critical for characterizing the impacts of climate change. In fact, one of the first steps that we need to take in order to be able to characterize how these events are changing in a warming world is to actually identify and track them in large data sets. We've seen a host of very disastrous, devastating extremes over the last few years, and they're only increasing in intensity, in frequency, and impact. So I think the challenge for us is to really be able to track these reliably in large data sets. This is a simulation that I borrowed from one of Mike Pritchard's presentations, an animation by, Murat, and this shows the very high resolution dynamics of the atmosphere. As you can see, there's a wide range of scales. There's organized structures across all scales. And there's really a lot of complexity, but besides all of the chaos that we see here, there's also a lot of different patterns of significance. And these patterns are extremely important for predicting how extremes might impact different parts of the globe. So how do we actually detect extremes of different kinds and patterns in such large complex data sets? This is a problem, of course, that's been studied and people have been working on this for decades. Most traditional methods in climate communities have used essentially empirical algorithms, which have threshold conditions, which are essentially heavily hand-engineered features of these events that are encoded into some sort of algorithm. And these are used to apply to different data sets to try to extract these events. The challenges are that these threshold conditions are subjective. They depend on the climate regime that we're in. They depend on geographical regions, the resolution of the data, et cetera. So they're very sort of hyper-tuned to specific types of data sets and regions and climates. They also don't scale well on large data sets and don't generalize well to new scenarios. The snapshots that I've shown here are essentially review papers that look at a host of different algorithms for different types of events. This has been done for atmospheric rivers, for extratropical cyclones, tropical cyclones, and so on. And I think the overarching conclusion is that there's a very wide diversity of results across these different algorithms, some order of magnitude in terms of the rainfall, in terms of the impacts, and so on. So this is a hard problem that needs to be reconciled. And the methodology that we proposed a couple of years ago was why not use deep learning for this problem, because deep learning is very well poised for pattern recognition types of problems. This is probably a slide many of you have seen many times now, so I won't get into great depth, but classification, localization, object detection, and segmentation are classic problems in computer vision and deep learning. We can essentially translate the same types of problems for climate science. I'll focus on segmentation, which is essentially using a deep neural network to classify every single pixel of an image into a particular class, so you get tight boundaries of events. There are differences in using these sort of off-the-shelf models. Climate data is multivariate. We have a wide range of scales. We'd like to apply this on data with different modalities and various other artifacts, noise, missing data, and so on. So there's quite a few challenges in adapting these methods for weather and climate data. But perhaps the biggest challenge is building a reliable training data set. Many of these methods require large amounts of data, and reliable labeled data is extremely scarce in climate science. Many other fields in the sciences have sort of tried to tackle this problem by essentially building their own expert labeled data sets. Obviously in computer vision, ImageNet was sort of the big data set for the deep learning breakthroughs that we've seen in the last 5 to 7 years. but also across the other fields of science in physics, in protein structure, astronomy, genetics, and drug discovery, and so on. People have essentially gathered together as a community to create high quality labeled data sets. So that's sort of the biggest challenge that we've had so far in the climate community. And we tried to address that by developing the ClimateNet dataset, which is a community-sourced expert labeled dataset. This cartoon sort of shows the workflow for what this looks like. On the left, we have the ClimateNet dataset, which is essentially a compilation of human labeled patterns. It could be class labels, bounding boxes around events, or tight boundaries, segmentation masks. We did this for tropical cyclones and atmospheric rivers, and we're aiming to expand this to various other types of events. This is all fed into a unified deep network that is trained to identify all of these different events simultaneously. And in Inference, we can apply this trained network to model output, satellite data, observational data sets, and so on to extract segmentation masks. So the first step in actually acquiring these labels is to have a labeling tool. And so we developed something called the Climate Contours labeling tool, adapted from the Label Me software that was developed at the MIT Computer Vision Lab. As you can see here, we have a snapshot of a particular time instant from a climate data set. We have different variables that are provided to the user, the climate scientist, that then sits down and labels different types of events. We have guidelines on what these events look like, how they're characterized, and of course the expert uses their expertise in doing this. This is a very tedious task, and we've conducted campaigns at over 10 different venues, both nationally and internationally, to gather sort of wide expertise in labeling atmospheric rivers and tropical cyclones. And the first results that we have, which is for about 10,000 events across various different snapshots of climate data, of course fueled by large amounts of coffee and pizza, is shown here. This shows the diversity of labels, and what's really interesting is that even amongst the experts, we have quite a wide variety of ways in which people label these events. And we believe that this actually encodes the different ways in which we think about these events. I think it's worth noting that these events don't actually have rigorous theoretical definitions, and there's a subjectivity in definitions of atmospheric rivers and tropical cyclones and various other events. So we capture that diversity in these labels. This is then used for training a segmentation model. On this graph, we see various different segmentation models in the computer vision community that have been developed over, say, the last decade. On the top right is a very large and complex model, DeepLab v3+, which was actually one of our earlier choices in 2018. And this was scaled out to 27,000 GPU nodes, and it turned out to be a good model for segmentation. But since then, we also learned that we didn't actually need the most complex model available. We could get away with simpler models that perhaps had some different features that were actually quite useful for detecting these events. So the choice that we made for this particular set of results that I'm going to present is CGNet, which is a context-guided network, the details of which are shown here. It's essentially a segmentation model that uses convolutions at different scales. So the context guiding block is what is sort of the key part of this network. It looks at convolutions not just around the object, but sort of at different ranges of amplification or zooming in or zooming out, whichever way you want to think of it. So the context guided block is not only getting a sense of what the object is, but also what's around the object as you expand out. So that's sort of the key element here. The loss that we use for training this architecture is what's known as a Jacquard loss, which is an intersection over union. And that's generally quite useful for characterizing such events. In inference mode, once the model is trained, we applied it to two very different scenarios. One is a climate change scenario. So I should note that the model itself was only trained on the present day climate with labels from the present day, but we apply it to a climate change scenario and also the satellite observations to see how well it generalizes. So the first set of results I'm showing you here are the application of the model to a climate change scenario from the same climate model. As you can see, the atmospheric rivers are the sort of long structures in the tropics to extratropics, and then the tropical cyclones are the kind of circular structures. It does a fairly good job of identifying both hurricanes and atmospheric rivers, and also sort of tracking their evolution over time. But I think what was most interesting is that we applied this to observational data without retraining it. So this is the same model trained on present day climate data, but it's applied to observations. And as you can see here, the results are still quite convincing. The atmospheric rivers are being tracked over time. You see the sort of the formation of these events and the evolution. There are some artifacts with the breaking up of events and some small structures that are recognized that are not quite atmospheric rivers or tropical cyclones, so there's definitely work to be done. But the first set of results is quite compelling. Moving on to the next slide. What was also really interesting is that the observational data had a different instance, but the model is still able to provide a segmentation mask that looks continuous and doesn't seem to break up despite having missing data. So that's another interesting result that we weren't quite expecting, but it turns out that the model is robust enough to work with small amounts of missing data as well. So how do we use such results? Well, one thing that we can do with very high precision segmentation masks, pixel-wise segmentation masks, is that we can characterize very specific things such as the change in extreme rainfall at a specific location on the globe because of climate change. This is just showing you one small set of results. There's more in the GMD paper that was recently published. This shows the change in the distribution of extreme rainfall because of climate change, and on the right are the scaling of the rainfall across different percentiles. And these results were corroborated by process-based studies that have been done on the same types of processes. So it's quite satisfying to see that we can not only get some very highly localized, precise information on the change of rainfall and things of that sort, but also that they corroborate findings in the literature. So where do we go from here? One important sort of extension of this is to be able to do this for other types of weather and climate patterns. As we know, I mean, there's a host of different patterns that are of importance. So we've only shown this for two types of events here. So we're collaborating with folks at NCAR and the European Space Agency to extend this to a wide range of other weather and climate phenomena. Another important question is quantifying the uncertainties. And given that we have multiple people labeling the same event, we can actually generate probabilistic segmentation masks, and collaborators at the lab are developing probabilistic segmentation techniques in order to not just provide segmentation results, but also the uncertainties associated with these masks. So at this point, I will dive into the second topic, which is a slightly different topic, but also I think of great importance for us as weather and climate scientists, which is enhancing the resolution of data. The topic is physics-constrained space-time super resolution of complex flows. That's a bit of a mouthful, but the key parts are there are physical constraints here that are being incorporated into the model. It's not just spatial super resolution, but also temporal. So we're enhancing both the spatial and temporal resolution of the data, and it's applied to turbulent flow. This is called Meshfree FlowNet, and this is in collaboration with several folks at UC Berkeley. Max was the one that led this project, a graduate student, well, now graduated from UC Berkeley, but also with collaborators at Stanford, Caltech, and NVIDIA. So the motivation for this is probably clear to many of you, but high resolution simulations of complex systems are extremely expensive. it's almost impossible to run very high resolution simulations of the weather and climate systems for long periods of time, simply because of how expensive they are. But we do need to have very high resolution data to make good assessments of the impacts of extremes, but also for various other planning and decision-making purposes. For example, on the bottom left is the image of taking in IPCC climate model output, which is typically at about 1 kilometer or so resolution, and trying to produce very high resolution outputs that can then be used for, say, planning for water or extremes, et cetera, in localized regions like, say, the Bay Area. On the right is a graph of accuracy versus computational cost for simulations such as atmospheric simulations. Low resolution simulations are at the bottom left, so low computational costs and correspondingly low accuracy. On the top right are very high resolution numerical simulations like the one we saw produced by the high resolution atmospheric simulations, but these are very expensive. They have high fidelity and high accuracy, but extremely expensive. So the question we asked is there a way to produce potentially high accuracy output with low computational cost using deep learning? And that's where Meshfree FlowNet comes in on the top left. There are a range of other multi-scale and model-based approaches that sit somewhere in between in the spectrum. So the specific context for this project was Rayleigh-Bénard convection, which is an important process in the atmosphere for turbulent convection and the formation of clouds, but also in the ocean. Many of you are probably familiar with the dynamics of these systems. It is an idealized problem, but it sort of is a step towards building these types of models for realistic simulations. So just to set the stage, the Rayleigh-Bénard convection problem is idealized as having a hot plate at the bottom and cold plate at the top with sufficient temperature difference between the bottom and the top, and instability is triggered that ultimately leads to turbulent flow. You have these convective rolls, but also a wide range of other structures. The non-dimensionalized equations that characterize this problem are the Navier-Stokes equations, and the non-dimensional numbers that govern the processes here are the Rayleigh number and the Prandtl number. On the right is a snapshot of what the solution looks like at a certain instant in time. As you can see, for the temperature, pressure, and velocities, there is some organized coherent structures, but there's also small-scale turbulence. So the Meshfree FlowNet solution that we proposed has a few key characteristics. First of all, it's a mesh-free super-resolution framework, meaning that it doesn't depend on a particular structure for the data sets. You can essentially provide super resolution outputs at any locations in space and time. It can be constrained by the governing PDEs of the system, so it's physics constrained. It's trained on fixed sized inputs, but it can be sampled at arbitrary locations in space and time, so you can produce essentially outputs of different spatial and temporal resolutions. And finally, it uses a fully convolutional encoder, so you can train on crops, but then apply it on very large domains by simply rolling out the convolutions. Just getting into a little bit of detail, I won't be able to go into every specific aspect, but just to give an overview, excuse me, you have inputs, which are low resolution inputs, and this is fed into first a context generation network, which is a UNet, and that produces a latent context grid. The key aspect of this is that it encodes the local correlations. So it's sort of building in the local spatial and temporal correlations that exist in the flow. This is then decoded using a continuous decoding network, which maps X, Y, Z, and Z to the physical outputs. So the continuous decoding network essentially gives you the spatial temporal functions that give you the actual physical outputs at any given location. The way in which it's trained is you can query at different locations in space and time, and you can essentially compare the predicted values versus the actual values to give you a prediction loss. And you can also apply equation constraints, PD constraints to have an equation loss. And together, this provides the total loss function for the network. Another key aspect of this particular framework is that thanks to the continuous decoding network, which is just a multi-layer perceptron, using backpropagation, you can compute very accurately the derivatives, and therefore you can apply PD constraints. The loss functions, as I mentioned, are the equation loss and prediction loss, and these are combined together using hyperparameter gamma. The continuous decoding network works as follows. The key job is to essentially model this spatial temporal equation given x, t, and c the context to give the physical variables u. Well, u naught refers to u, v, and p. So this is what the actual network looks like, a multi-layer perceptron. And because we query at arbitrary locations, which may not be on the exact locations of the high-resolution output, we interpolate trilinearly to get the values of the physical variables of that location. And by using backprop, we can enforce PD constraints on this particular data set. So putting that together, this is the actual details of the different pieces of this Meshfree FlowNet framework. I won't get into the every single aspect of this, but basically it's a unit for the context generation network. And then the baseline that we compare against is a standard convolutional decoder, which is often used for super resolution. And ours is the continuous decoding network, which uses both the latent context grid, but also the point coordinates to produce the outputs. So the training process is as follows. You have data x, y, or x, z, and t. We take crops in space and time, and we essentially downsample that to 8x smaller resolution to produce the low resolution data. And the high resolution data is interpolated at these query locations to get the random samples that are used for training. And the training setup is once we take the low resolution data and pass it through the unit, we have a latent feature grid or the latent context grid that's queried at arbitrary locations. And then through the implicit network, we get the predicted values. The ground truth is interpolated from those query locations. So we have the actual ground truth values. Comparing the predictions and the actual ground truth, we have an L1 loss, and we also have the PD loss using backprop. So this shows the results for one particular case. On the top row are high resolution ground truth. At the bottom row is the actual super resolved predictions. In the middle is the low resolution inputs. It's quite remarkable that the model predictions are almost indistinguishable from the ground truth. And as you can see, there's enhancement of resolution both in space and in time. We evaluate this model on a range of different metrics that are used in the turbulence modeling community, the total kinetic energy, the RMS velocity, dissipation, Taylor microscale, Taylor scale Reynolds number, Kolmogorov length and time scales, and the integral scale and large eddy turnover time. So it's a comprehensive set of sort of physics-based metrics for evaluating the performance of the model. This shows the R2 scores and the normalized mean absolute error for Meshfree FlowNet versus baselines. At the optimal hyperparameter gamma star, that's the weight between the PD loss and the L1 loss, we get a performance of 0.9981, which is significantly better than the baselines. But perhaps most interestingly, we tested the generalizability of this model on two different types of scenarios. One is on unseen initial conditions. So we trained the model on one condition and then tested it on a different one, trained it on 10 initial conditions and tested it on a 11th different initial condition. And we get very high R2 scores. And for unseen boundary conditions, we tested the model that's trained in the regime of 2 to 90 times 10 to the 5 Rayleigh number, which is the block in green, versus regimes that are 2 orders of magnitude smaller in Rayleigh number and 2 orders of magnitude larger. And we find interesting results on both sides. As you can see, the performance is quite good for a wide range of Rayleigh numbers. So this sort of shows that the model not only performs well in the given regime, but also in sort of new unseen conditions. And finally, we scaled this out to a large number of GPUs. We have the scaling plot on the top left, or I guess on the left. And we get about a 96.8% scaling efficiency up to 128 GPUs. The loss curves are in B and C, and I'll sort of skip over this for the sake of time. So where do we go from here? This is, of course, a rather simplified system and kind of idealized, but we would like to extend this to more complex systems and three-dimensional flows. We're also coupling these super resolution models with traditional PDE solvers. One thing that I sort of skimmed over was that we downsample the high resolution data to produce the low resolution data. But of course, this is not exactly the same as running a solver at low resolution. So in sort of follow-on work, we've extended this to actually couple a low resolution solver with super resolution to produce high resolution data, which corrects for not just the resolution, but also the trajectory of the simulation. And finally, we're also combining super resolution models with neural PDE solvers in collaboration with folks at Caltech and NVIDIA. There's been some very interesting work that Anima Anand-Kumar and her group have done recently on actually solving these complex PDEs directly using neural networks. And one approach is to use those solvers coupled with super resolution. So it's sort of end-to-end deep learning-based solutions for these PDEs. So we're at about 30 minutes and I have a few minutes left. So I'd like to maybe speculate a bit on the future of machine learning for weather and climate. Of course, this is some personal opinions and not necessarily combines every single person's outlook on this, but in a sort of way to speculate and maybe provide some provocative ideas on where we could go. I think physics-informed machine learning is going to be increasingly important in the future. This has already been described a little bit by Professor Vipin Kumar last time, but I just wanted to summarize a few key reasons why I think physics-informed machine learning is going to be critical. We do need to build physically consistent and scientifically sound predictive models, increase data efficiency, accelerate the training process, improve generalizability, and enhance transparency and interpretability. And I think one of the most compelling ways in which all of these challenges can be addressed simultaneously is by trying to incorporate domain knowledge and physics into machine learning models. There are many different ways in which this can be done. We saw a few 2 weeks ago, and I presented one particular topic here, which was using custom neural network architectures. 2 weeks ago, Professor Kumar talked about physics-based loss functions, which can be used. We also saw that in Meshfree FlowNet. You can build custom networks to impose specific properties of these systems, such as local correlations or multi-scale properties and so on. We've also seen this from Tom and his collaborators using conservation layers for neural networks to enforce analytic constraints and several other pieces of work. Many of the systems that we work with in the atmospheric sciences, or actually across weather and climate, have symmetries in them, and incorporating these symmetries can be an important way of incorporating physics. We've seen examples in turbulent flows in physics, chemistry, and elsewhere. I think that's a very exciting area as well. Stochasticity is an important property of the weather and climate system. Even though the governing equations are deterministic in many of our subgrid scale models and other simplified models of these systems, we do need to incorporate stochasticity in order to better capture the properties of the system, the scaling laws, but also to improve scale and reduce bias. There are many different ways in which we could incorporate stochasticity in these models. Some ways have been shown in simpler systems using generative adversarial networks, probabilistic models, ensemble neural networks, and so on. Stability is another big challenge, especially in models where you incorporate, say, a parameterization that's a machine learning-based parameterization into a larger model, such as a weather or climate model. Noah Branowitz and collaborators have shown how stability can be achieved, or at least stability challenges can be understood using tools from dynamical systems theory. And perhaps there are ways in which we can design networks that are stable when coupled with larger PDE systems. So I think there's work to be done there too. All of the systems that we work with are multi-scale. Some of these can be explicitly encoded using things like the covariance function and properties of the spectra into the neural network directly. Or we could use other sort of clever designs of architectures to incorporate these multi-scale properties. And then finally, there's a wealth of knowledge that we have from decades of research in physics-based modeling, and we don't need to sort of discard all of that and start from scratch using neural networks. In many papers, I think we've seen arguments for how we can build on top of physics-based models by replacing certain components using neural networks, or perhaps replacing empirical parameters by trained or learned parameters from neural networks. One example that I show here is in LES, we can use neural networks to essentially build learned spectral filters that are more accurate than sort of classical Smagorinsky type models. So there's a host of different ways in which physics can be incorporated. I think it's still a very young field at this point, and it's not clear as to exactly how, sort of what the best strategy is for doing this, but I think that also means that there's lots of exciting research to be done. I'd like to conclude with a few challenges. I think as a community, we have to try to characterize and quantify sources of uncertainty, train models with data characteristics such as missing data, noise, etc. Promote model consistent training, so train our networks in ways that are consistent with the assumptions of the particular model which we're developing, derive our estimate stability and convergence properties, and importantly, evaluate the fidelity of these models on extremes. Other challenges besides the scientific challenges to really make these successful are diagnostically, we don't actually have standardized evaluation techniques and benchmark data sets and problems. Stefan Rasp and others have started to develop this with WeatherBench, but I think there's a strong need for having ways in which we can intercompare the different types of machine learning models that we develop in sort of systematic ways. Computationally, scaling these models is quite challenging. We've shown that many of these models work on smaller problems, but to make them really useful for large-scale problems, we'd like to scale these up on large machines and large data sets. And of course, the reason we have this sort of data science seminar and working group is to bring together people from different communities, and I think that is also a big challenge. For these to be truly successful, we need to have collaboration across the sciences, computer science, statistics, AI, and so on. So I think I'll conclude with that and say that it's great to see a sort of rapid explosion of the different workshops, conferences, and summer schools in AI applications in weather and climate and the sciences in general. And I look forward to seeing many more of these in the coming years. Thank you.
Great, thank you, Karthik. So in the interest of time, let's just keep for the next 20 minutes, we'll have a public Q&A question or Q&A discussion. So if you have a question, reminder to use the raise your hand button, which is located next to your name, or you can type your question into the chat box if you have any audio problems. So with that, any questions for Karthik? I see a question from Wang Zhao. Sorry if I mispronounced your name. Go ahead and unmute yourself.
Yep. Thanks for the great talk. Very interesting. So I have a question. What do you see are the challenges to be tackled in order to apply the method you presented in the project 2 for triple simulation to the actual real world problem in project 1?
Oh, interesting. Thank you. Yeah, that's an interesting question. Well, so I think, as I said towards the end of the second deep dive, We've shown that this technique of super resolution works well on a simpler sort of data set with relatively small amounts of, there's a wide range of scales, but not as complex as the full-blown climate system. So I'd say the next step in actually making space-time super resolution useful for actual weather and climate models is to test them on three-dimensional flows. So this is first, we've shown this on 2D flows. We'll have to extend it to 3D. The next thing is, it is a sort of artificial problem in the way in which we've developed the low-resolution data set, because we essentially low-pass filter the high-resolution data to produce low-resolution data, and then super resolve that to compare it against the actual high-resolution data. As I mentioned again in the outlook, the key challenge will be to run a model at low resolution and then couple that with the super resolution. So we have at every time step super resolved outputs that can be used to correct the low resolution simulations. So it follows the right trajectory of the high resolution output. So there you have a fully coupled super resolution with PD solving that needs to be done. So that's work in progress. So I think that would also help us get closer to really applying this on much larger models.
Thank you.
Welcome.
All right, we have a question in the chat box from Ime. She's kind of picking your brain a little. What are the best ways to address uncertainty in machine learning?
Well, that's a hard question. Thank you. Well, there's a few. I think in the first part I mentioned probabilistic segmentation as a way we're using different human labels to characterize confidence levels of the boundaries of these events. So I think in pattern recognition, that could be a promising approach. There's also a host of other ways using Bayesian neural networks, so having distributions for the weights as against just deterministic values. I think there's some work that's being done in that as well in the climate community. Besides that, ensemble neural networks is perhaps another approach where we use an ensemble of models to characterize uncertainties. Concrete dropout, which is also, I guess, Monte Carlo dropout is what some people call it, is another way where different weights are dropped in either in training or in testing or in both. So that's another way to characterize uncertainties. So yeah, there's definitely a few approaches that have been developed. I'm not too sure that many of them have been applied to weather and climate applications, but I think there's a lot of scope there.
She says, great summary, thank you.
Thank you.
Another question in the chat box by Mara Majdi. Is it possible to develop a machine learning model to have low resolution data from high resolution data?
Oh, interesting. So that's the opposite of super resolution. Well, I mean, sure, you could. I guess you could also low pass filter. You could do coarse graining of different kinds. Maybe I might sort of flip that question back to you, saying what is the application? What's the goal? Because in some ways you're using a machine learning model to compress and discard some information to produce low resolution output. So I guess, well, my answer would be that it really depends on the application that would determine what type of machine learning model should be used. But there are a host of different non-machine learning based ways as well to do that.
Okay. A question in the chat box by Gavin D. Are physics-informed machine learning, do they extrapolate well?
Yeah, so yeah, that's a good question. Thank you. Well, that's one of the objectives for incorporating physics into these models is to improve their extrapolation properties. And the motivation for that is the governing laws of the system or the physical properties are obeyed irrespective of what the regime is. And so by incorporating these properties into machine learning models, we can try to help them generalize better because black box machine learning models that do not have these properties don't generalize well because they don't exactly satisfy these constraints. So my answer is yes. Many of these models do show better generalizability, but it's not all done. There's definitely a lot of examples where they can fail, and I think that's exciting because we need to fix those.
Any other questions for Karthik? All right, Tom, I see you have some questions. Go ahead.
Thank you for a great talk, Karthik. So I had a question, which is, in which cases do you think physics-guided machine learning is ill-advised? So, an example I can think of is when you can't close conservation laws on any true data set. But I was wondering if you had found other notable examples. And for instance, would you really call your first example on ClimateNet physics-guided, or is it just human-guided? I mean, for sure based on physics, but are there actual physics guiding it, or is it just human knowledge that you collected?
Yeah, great. Thank you. There's like 3 questions in there. But yeah, so first of all, maybe answering the last question first. The first part of the talk is sort of implicit in the sense that we're using human labels and the humans have expertise about the physics of the system. So there isn't explicit physical constraints that are imposed in that particular project, in that model. So it's not quite the same as more explicit physics-informed models. So that's the first response. The second is, where would these physics constraints potentially not be helpful? That's really interesting. I think one obvious thing that comes up is sometimes you do see a decrease in performance of these models on whatever, mean squared loss or other metrics that you might have when you incorporate physics. So there can be a trade-off between satisfying physical constraints versus accuracy and performance on a particular objective. And in some cases, depending on the final application, we might care more about the accuracy, even if we don't necessarily obey all of the physics. So in those cases, I think it really has to be driven by what the ultimate application is. If accuracy is more important, then we might need to compromise on some physical constraints. I don't know if that answered the full question, but if there's other parts, I'm happy to.
No, it answers the full questions.
Okay.
Thank you.
We have another 10 minutes for questions. Another question from Gavin D. How does the required number of training samples to optimize vary with different physics-guided techniques?
Thank you. Yeah, that's a great question. So the number of samples does decrease, and I didn't show that quite in this particular talk, but in previous projects I've shown that by having physical constraints, we can decrease the number of training samples to almost 1/10. So with 10% of the training data, you can still achieve the same accuracies. So I guess an intuitive way to think of it would be that the physical constraints helps reduce the set of options available for the machine learning model, and hence optimizes better towards a good model much more quickly using much fewer, far fewer training samples. Although, I mean, that's not necessarily a rigorous value. I think it really depends on the problem. In some cases, you might get much better decrease in training samples, or in some cases, it might not help that much. So, but in general, I think we expect that having physical constraints does help reduce the number of training samples.
Right, he says thank you.
Thank you.
A question from Galen Vincent. Besides turbulent flow models, what are some more specific areas you think physics-based loss and these other methods to incorporate physics could be useful in climate science?
Sure, yeah. I mean, if we look back at Professor Bipin Kumar's presentation from 2 weeks ago, I think they had similar approaches using physics-based losses applied to hydrology, to lake temperature modeling. I've seen this applied in ecosystem dynamics. Pretty much across the board, physics-based loss is probably the easiest way to apply a physical constraint. There's obviously no guarantees on the actual constraint being satisfied because it's only sort of a loose constraint or a soft constraint, so to speak. But you can apply it to different types of systems. I think things get a little more challenging with exact satisfaction of these constraints using custom architectures. Things are a little more tricky, but the physics-based loss, I think, is very straightforward to incorporate on pretty much any type of problem, as long as you have a physical constraint that needs to be satisfied.
Okay, question from Mike Pritchard. I see that your hand is raised.
Hey, can you hear me?
Yes.
Okay. I just wanted to ask you a question based on your proximity and ties to people doing high performance, ambitious machine learning. Do you have an instinct for, like, in the two limits where you have a machine learning problem that just has like ridiculous data amounts and you want to coordinate a bunch of GPUs to work on it together? The best tools these days are student-friendly tools. And in the other limit where you want to train a model that's bigger than a GPU can fit in its own memory. I know those tools are evolving rapidly, but curious for your perspective or advice.
Wow, that's a good question. I must admit, I'm not an expert in scaling and sort of the computer science of these models, but I'll attempt to give some responses. For the second one, I guess model parallelism and data parallelism would be two things that you probably already tried. But that can be used if you have very large models that don't fit on a single GPU. For the first one, could you repeat what the first part was, if you don't mind?
Well, just when you have like billions of samples or really large training library,
Yep.
to reduce the time per epoch by carving up. It's not the model fits on an individual GPU, but the training samples are large.
Yeah, well, in that case, I guess data parallel would be the way to go, where you sort of break up the data sets into smaller chunks, and there's clever ways of combining the results that come out of the different chunks. But yeah, I think my first response would be using some sort of data parallelism, and I think PyTorch and several other, well, TensorFlow and others have. There's distributed frameworks for doing that that you also probably tried out.
Okay, there's a question in the chat box from Wang Zhou. It's a multi-part question though, so I don't know if you want to also pull it up. So the first question is, how is the low resolution input generated? Is it averaged from high resolution simulation? And if so, is the network learning simply the reverse of averaging? And can it be applied to data where low resolution data is from simulation directly?
Yeah, that's a great question. I tried to hint on that towards the end. Yes, so the low resolution data is generated by low pass filtering the high resolution data. And so it's not averaging, but it's low pass filtering, and the network, you could argue, is essentially just inverting the low pass filtering operation to produce the high resolution outputs. So if I were to apply this model as it is on a real low resolution data from a low resolution simulation, the outputs will not be physically as well. Let's say it's not going to be as accurate. The reason for that is the low pass filtered data is not quite the same as an actual low resolution simulation data. The statistics of the data and also the trajectory on which the low resolution simulation is traversing are very different. So how would we fix that? I think the right way to do it, or at least one of the approaches to doing that more accurately, is to couple at every time step the outputs of the high resolution, correct for the low resolution trajectory, take the next time step in the PD solver to produce the next low resolution data point, super resolve that to get high resolution data, use that super resolved output to once again correct the trajectory and so on. So it would have to be a fully coupled super resolution with the PD solver to really get results that are accurate. But as a sort of proof of concept, we've shown that if you have low resolution data that's produced by low pass filtering, you can do this. But yes, I agree that this is a critical question.
It says thank you. Question from Ime. Do you prefer PyTorch or TensorFlow, and why?
Yeah, good question. I started using TensorFlow mainly because most others were using TensorFlow at the time. This was 2.5 years ago. And then quickly switched over to PyTorch as the libraries and the tools and kind of just the wider range of applications that were available, a lot more examples, better sort of resources to help debug and so on. So I think at this point, I would prefer PyTorch over TensorFlow, but that's pretty subjective.
Great. Any final questions? Ema says thank you.
Hopefully there's no one from Google that's on this call.
Right. I don't see any movement and nothing on the chat either. Ema does thank you for a great talk. She's a member of our working group. So I think we can end it here, end your webinar here. So thank you so much, Karthik, for today's talk. So for everyone that's on here, a recording of his talk will be shared later this week. And then our next webinar will be on February 8th, which will feature Michael Brenner of Harvard University. So if you have any questions up until then, feel free to reach out to me, Karthik, or Tom. So yeah, thank you everyone for joining today.